So today we discuss about a very important and very interesting question from group theory. A4 has no subgroup of order 6. We know what is A4. A4 is a alternating group, also a subgroup of S4. We know what is S4. Uh, Before I proceed, I assume that we all know about the symmetric group S4 and the alternating group A4. Then we proceed for proof this question. This is a very interesting question, and after prove this, we can conclude a very important result. So, uh, first I define what is A4. A4. We all know that A4 is a subgroup of S4, the symmetric group with 4 symbol. Okay, so what is A4? A4 is a set of all even permutation of S4. See, before we proceed, I already assume that we all know about what is A4, what is S4, what is a subgroup, what is the order of a group. I assume that we all know that. So S4 is the set of all even permutation of S4. We know that S4 is a symmetric group with 4 symbol, and also we know that order of S4 that equal to 4 factorial, that equal to 24. And we also know that order of A4, so first define, we know that order of A4 is a subgroup of S4. Order A4, the alternating group, contain all the even permutation of S4. Even permutation means even number of transpositions. What is transposition? Transposition is length of 2 cycle. This is transposition. So what is A4? A4 is the collection of all even permutation of S4, and even permutation means even number of transposition. Transposition means 2 cycle. Okay, so we know that A4 is a subgroup of S4. Then what is the order of A4? We know that order of A4 that equal to order of S4 divided by 2, that equal to 12. Okay, so what do we get from here? We get that order of A4 that equal to 12. Okay, we know that order of S4 equal to 24, then order of A4 is 12. Okay, so let me write this. So we get order of A4 that equal to 12. Okay, now what is our target? Our target that A4 has no subgroup of order 6. Okay, so what is our target? Our target so A4 has no subgroup of order 6. So this is our target to prove. So we prove this by contradiction method. Okay, so we assume that, so we proceed this by contradiction method. So firstly we assume that A4 has a subgroup of order 6. We assume this and we see what will be the contradiction. Okay, so let us assume that H be a subgroup of A4. So H be a subgroup of A4 and order of H that equal to 6. We assume that why? Because we want to prove this statement, this problem, by contraction method. So we assume that A4 has already a subgroup, that is H, of order 6. Okay, and now see, we also know that S4 has one length cycle, product of two length cycle, three length cycle, and four length cycle. So we know that in S4 three length cycle, the number of three length cycle is 8. We know that. So there is 8 element of 3 cycle. Okay, so think, so see carefully what I am saying, that we assume that order of H equal to 6. What does it mean? It means that without identity there are 5 elements in the subgroup H. Okay, and we know that S4 has 8 three length cycle, and we also know that any three length cycle is a even permutation, because we can reduce it, this three length cycle, to transposition, that is AC. We can write this, and AB, this is a transposition, this is a transposition, and number of transposition is 2. So this is a even permutation. So since this is a even permutation, then this cycle is obviously belongs to A4, because A4 is the set of all even permutation of S4. Okay, can you understand what I am saying? So let me repeat what I am saying. So see here, order of A is equal to 6. Okay, then what does it mean? It means that other than identity there are 5 element in the subgroup H. Okay, and we know that in S4 there is 24 element in S4. Okay, but 24 element in S4, but there are 8 element of 3 cycle. There are 8 element of 3 cycle, and the 3 cycle forms a even permutation. Understand? The 3 cycles forms a even permutation, because we can write 3 cycle into 2 transposition. See here, I am writing this. So if I take a 3 cycle from S4, I take this belongs to S4. Okay, A, B, C, these are 3 length cycle. I can write this AC, AB. This is a AC, this is a transposition, that means 2 cycle, and AB, this is a transposition, that means 2 cycle. So number of 2 cycle we get 2, that is even. So the total 3 length cycle is a even permutation. Since this is a even permutation, then this three cycle goes to A4, because A4 is a set of all even permutation. Similarly, what I am saying, similarly there are 8 3 cycle in S4. Okay, there are 8 3 cycle in S4. Then can we say that all the 3 cycles belongs to the subgroup H? See here. So just a second. So since H is a subgroup of A4, okay, we assume that H is a subgroup of A4, and we know that we define A4. What is A4? A4 is the set of all even permutation of S4. Okay, so all the elements are even permutation in A4, and H is a subgroup of A4. Then obviously the elements of H also are even permutation, because H is a subgroup of A4, and A4 contain all the even permutations of S4, and H is a subgroup of A4. Then obviously H contain all the even permutations of A4. Okay, so what we say here? We say here that H is nothing but the collection of even permutations of A4. Okay, so we see here there are 8 elements of 3 cycles. So the 8 3 cycles, A, B, C. Okay, this belongs to A4, and see here, order of H that equal to 6. Then there, other than identity, there are 5 elements. Okay, if 8 cycle, the number of 8 cycle, the 3 cycles is belongs to A, is it possible? No. Why? Because order of A is equal to 6. If all the 3 cycles in A4 that belongs to H, then the order of H becomes 9, because they are identity 1 element and 8 others 3 cycle. So 8 plus 1 that equal to 9. So order of H is become 9, but we assume that order of H that equal to 6. So it is impossible that all the 3 cycles is belongs to H. So can you understand this, what I am saying? So all the 3 cycles cannot belongs to H. So there are at least 1 3 cycle. I am writing this, at least 1 3 cycle from A4 cannot belongs to H. Why? I hope you understand. Because order of A is equal to 6, and we know that the number of 3 cycles in A4 is 8. So if 8 elements is belongs to H, then there are 9 elements. So order of H that equal to 9, but we assume that order of H that equal to 6. Okay, so we write here that at least 1 3 cycle from A4 cannot belongs to H. So let this 3 cycle is sigma. Let sigma is a 3 cycle that such that sigma does not belongs to H. Okay, we assume that at least 1 3 cycle. So we assume that sigma is the 3 cycle that does not belongs to H. Okay, so see here, just a second. Okay, so we assume that we assume that sigma is a 3 cycle that does not belongs to H. Okay, now we claim that sigma square doesn't belongs to H. So if sigma square belongs to H, then that implies sigma square dot sigma square obviously belongs to H, because the closure property, because H is a subgroup, so closure property hold. That imply we can write it as uh, sigma cube into dot sigma that belongs to H. Okay, that imply we know that we already assume that sigma is a 3 cycle, so sigma to the power 3 that becomes E, that is the identity element sigma that belongs to H. So you can understand here sigma is a 3 cycle. Okay, so sigma to the power 3 that becomes identity. If we operate sigma 3 times, then it gives identity, because it is a 3 length cycle, order of sigma is 3, so that sigma cube that equal to E, that imply sigma belongs to H, which is not possible. Not possible, because we already assume that sigma doesn't belongs to H, but we see here sigma belongs to H, which is not possible. Okay, so our claim is true, that is sigma square doesn't belongs to H. Okay, now see that we can construct a subgroup. So I am writing here, so we can say that there exists a subgroup namely K. Okay, K that equal to, the elements are identity, okay, sigma and sigma square. Okay, so see here that sigma doesn't belongs to H, and we already proved that sigma square also doesn't belongs to H. So we take identity sigma and sigma square, and we construct a set with 3 elements, identity, sigma and sigma square, and you can easily check that the set K is a subgroup of A4. Okay, so we get another subgroup namely K. Okay. And now we know a popular result that is order of HK that equal to order of H into order of K divided by order of H intersection K. Okay, this is a very well known property result. Just a second. This okay, so that imply order of HK equal to order of H, we already assume that 6, and order of K there are 3 elements, so 3 divided by, so we already proved that sigma doesn't belongs to H and sigma square doesn't belongs to H, so these two subgroups are different, so intersection will be identity, that is 1, so this is equal to 18. So from here we get that order of HK, okay, that equal to identity, sorry 18, order of HK that equal to 18, but so we get order of HK that equal to 18. Okay, but but we know that what we know that HK is a subgroup of a subset of S4, sorry, A4. HK is a subset of A4. Then order of HK less than obviously order of A4, that equal to 12. So we get order of HK equal to 18, that less than 12. Not possible. So this is a contradiction. So our assumption is wrong. So what we assume? We assume that A4 has a subgroup of order 6, but we get a contradiction. So our assumption is wrong. So our assumption is wrong. Hence A4 has no subgroup of order 6. So this is our proof. Okay, so from here we can conclude. Just a second. So what we get? We get that A4 has no subgroup of order 6 of order 6. Now recall the Lagrange theorem in group theory. Okay, Lagrange's theorem. Lagrange's theorem. It says that if H be a subgroup of G, G is any group and H is a subgroup of G, and suppose order of H that equal to suppose A and order of G that equal to N, then A divides N. Basically Lagrange theorem says that order of subgroup divides order of the group. Okay, order of subgroup divides order of the group. Okay, now what about the converse part? I am saying that what about the converse part? So see here. So now our previous example A4, okay, order of A4 that equal to 12. We know that 6 divides 12, obviously 6 divides 12, but does A4 have any subgroup of order 6? The answer is no. A4 has no subgroup of order 6. See, the converse of the Lagrange's theorem is not true in general. Okay, we know that order of subgroup divides order of group. Okay, all right, but the converse part, if any number that divides the order of the group, is there any subgroup of this order? Answer is no. See here, see the group A4. Okay, the order is 12. Okay, and we know that 6 divides 12, but we already proved that in A4 there is no subgroup of order 6. Okay, that is the converse of the Lagrange's theorem is not true. Okay, that is our observation. So our observation is that converse part of Lagrange's theorem is not true. Okay.